In this video, I'm going to discuss a technique called separation of variables. You may have already seen the angular momentum problem. Well, if you go back and examine the angular momentum problem for the rigid rotor, well, first of all, the two coordinates, the variables are theta and phi. And if you look at the actual spherical harmonic functions y, L, m sub L of theta and phi, it's just a function of theta times a function of phi. So the theta functions are things like cosine thetas and sine thetas and so on. And the phi functions are these complex exponentials, e to the I phi and other things like that. Well, if you go back and look at the operator, the angular momentum operator, which can easily be converted to the kinetic energy operator for the rigid rotor, you can see that there's a term with theta derivatives only and phi derivatives only. And that's actually a necessary and sufficient condition to do the separation of variables. That's to say, if the Hamiltonian separates into a sum of one type of derivative and another type of derivative, then the wave function will be expressed as a product of one type of function and one coordinate variable, and then times a function of the other variable. And then when that's all said and done, the energies actually add together. There will be an energy that depends on the variable theta and an energy that depends on the variable phi. Now, if you go back and look at the quantum numbers for the rigid rotor, you have the quantum number L or capital J when it's used in molecule rigid rotors, and then m sub L. Well, the energy for this system does not depend on m sub L, so basically this is 0. And so the energy of the rigid rotor is basically only dependent on the quantum number little l or capital J, and it's L times L plus 1, h bar squared over 2 times the moment of inertia. All right, so that's, we're not actually going to derive that or anything. One we are going to derive is called the 3D particle in a box. So let's write down the particle in a line wave function. Okay, and so we'll call it x, because the one we did was for the linear momentum in the x direction. So we're going to call the dimension, the length of the box in the x direction, Lx. We're just going to add a little x subscript to the wave function. And so there's the n quantum number. Now it's going to be the quantum number for the x direction. Pi, of course, x is the coordinate over Lx. All right, and so there'll be two more just like that. It'll be psi y and psi z. So I'll put ditto, and the only thing that you change is this x to y, x to y, x to y, x to y. So 4 different places, then psi z. And the total wave function is going to be the product okay, I'm going to call it psi x, and so I'm just going to say nx and the position x. So there's different ways you can express this, but we'll just do it this way. Okay, so the variables are x, y, and z. So it separates into a product. Okay, so now what about the quantum numbers? Well, the math for every individual coordinate is all the same. So they're more or less independent of each other. So just like nx goes from 1 to 2 to 3, etc., up to infinity, so does ny independently of x. And so ny can be 1, 2, or 3. And so it doesn't matter what this one is, this one will be any one of these integers as well. So you can have 1, 1, or 2, 1, or 2, 2, or 1, 2, or whatever. And so all possible combinations. And of course, this third coordinate is the same. All right. So that's going to be the wave function. And now what about the Hamiltonian? The Hamiltonian, now why can we do this? It's because when we look at the Hamiltonian, it's going to be the Laplacian divided by 2m times h bar squared and minus. Okay, so it's minus h bar squared over 2m times the partial derivative with respect to x, second derivative, and y and z. All right, and so that's why it's separable into an x type of Hamiltonian and a y type of Hamiltonian, which would be minus h bar squared over 2m times second derivative of y. And so when you look at that equation, it's identical to the x equation, except the label x and y, and then this one as well. And then when you look at the energies, the total energy is going to be Ex. And so that's going to be given here. Okay, so the energy is going to depend on the length in the x direction, and it's going to depend on the quantum number n x squared. All right, so it's just going to be Ex plus Ey plus Ez. Okay, so now frequently people consider a cube where all the lengths are the same. So let's think about what happens in that case, is that there is no, so these are the equations for that. If there's no, if there's just a single length for all three, then everything else is still the same. And so when we look at the total energy, all this stuff is the same except for the quantum number n. H squared all right, so now we get something interesting, is that the number of states, of course, depends on, you know, how many different ways there are. So the lowest possible energy you can have, if this was 1, that is 1, and that is 1. And so when you do that, you get 1 squared plus 1 squared plus 1 squared, that's 3. So the energy of the ground state, which we might call, for example, psi 111. Okay, so the subscript would be just the integer nx, ny, and nz in that order. That'd be understood. And so the energy of 111 would be 3h squared over 8ml squared. Well, what's the next highest energy level? Well, the next largest number you can get from this is if you change one of these ones to a 2. You can change nx to a 2 and leave the others as 1, or you can change ny to a 2 and leave the others as 1, or you can change nz to 2 and leave the other 2 as 1. So it turns out there's 3 different ways, and they all have the same energy. So E of 211 is going to be the same as the energy of 121, and it's going to be the same as the energy of 112. But these are all distinct states. That is to say, psi 211 is not the same thing as psi 121. As a matter of fact, they're orthogonal to each other. And then the wave function for psi 112 is orthogonal to these two as well. So there's 3 unique, distinct states. They all happen to have the same energy by coincidence. So this is called degenerate. So this is threefold degenerate because there's 3 states. And so another word for threefold degenerate is triply degenerate. However, once you get up to a certain number, nobody wants a special name for, 16, which would be hexadecadegenerate or something crazy like that. And so what is 2 squared plus 1 squared plus 1 squared? That's 6. All right, and so you draw the energy spectrum, for the particle in a 3D box. The lowest energy would be 3, and then the next one would be triply degenerate. This is E, so it'd have a 1, 3 h bar squared, and then, so this would be E111, and then this would be E of 2, 1, 1, etc. All right, well, that's it for separation of variables.